Yes, tiny bit of echo, but hopefully that'll go over.
Yeah, I can see you from the back, which is a little bizarre, but it works.
Now? Okay.
That is, I can see you from the back of the room.
Yeah, so our next speaker is Professor Adam Smith from Boston University. Adam, we're keeping it informal, so take it away.
Okay. Hi, everyone. I'm sorry I couldn't be there in person. I much prefer, of course, to be there with you. I'll be talking about memorization in machine learning, and this is joint work with my student, Gavin Brown, or soon to be former. He's graduating and heading off to University of Washington as a postdoc. Mark Bunn, my colleague here at BU, and our collaborators, Vitaly Feldman and Kunal Talwar at Apple. I don't see the audience very well. I kind of have this weird back of the room view, as I said. So by all means, interrupt with questions, ask, I won't know when you're asking a question unless you speak up. So sorry about that. Okay, so, machine learning models contain information about their training data. I'm not telling you anything you don't know. And the question we set out to understand is sort of like, just how much information about their training data do they really need, and what exactly do we mean by even formulating a statement like that? So I'll talk about two papers, one that appeared at Stock 2 years ago now, where we show that in natural settings, memorization of nearly entire training examples is necessary for accurate learning, even when a lot of the details of these training examples are ultimately irrelevant to the task at hand. And I'll try to explain what I mean by that. And then the second paper looks at not so much sort of how much information does the model have to contain, but how large, what kinds of intermediate states do we need when we're training a model? And we give, again, what I claim are relatively natural problems, where every one-pass learning algorithm requires very large intermediate memory because of the need to memorize individual training examples. And again, I will try to explain what I mean by that when I get there. Okay, but I'll start with this first thing and I'll talk about it. And maybe I should start by saying one of the reasons I chose this topic for this workshop is both I find the results interesting and compelling, but they are both sort of very information theoretic in their kind of both in the statements, but also in the proofs. And so they kind of highlight the role that this sort of information theoretic perspective that the IT community brings to these problems can really be useful. Okay, so what do we mean when we talk about memorization in machine learning? Sometimes that's extremely explicit. Like, so for example, if I have a one nearest neighbor classifier as pictured on the left here, then the description of the classifier pretty much is the entire data set. And so like you're memorizing because that is what you want to do. And there are other models where it's so like almost as explicit, like for example, for support vector machines, the standard dual form description of a support vector machine basically consists of the exact descriptions of several data points in the space. But memorization is often also like an unintended side effect, or seems to show up as an unintended side effect of learning. So for example, way back in the days of GPT-2, before we had the current, even before we had the current very large models that are driving these chatbot AI interfaces, there's a paper looking at how GPT-2, when prompted with prefixes of training text, will like spit out as a suffix, a suffix which contains, for example, exact addresses from its training data. More recently, people looked at, stable diffusion, which is one of the, this is a specific instance of a stable diffusion model for generating images. And what you have on top and on bottom, on the top are generated images, and on the bottom are images from the training data set. And they match up, as you can see, nearly exactly. Okay, so these models that we're training, they pick up on all sorts of like individual features of their training examples, like very specific stuff. And one might conjecture that that's just a mistake, that it's because we're not training them the way we should, and maybe that's true in many cases. But there's also this kind of emerging understanding that overfitting in particular ways is often beneficial to the learning process. That sort of contradicts classical learning theory, circa 10 or 30 years ago, and so that you could sort of view our work as kind of fitting into that larger vein. Okay, so when I say memorization, I want to be clear that I don't mean just overfitting or like interpolation through the data in the case of a supervised model, right? So very often when people do talk about that, that's an important and interesting topic. So for example, classical machine learning theory says you shouldn't overfit. You should come up with these parsimonious models whose description length is far less than the entropy of the data set, or even of the label set. On the other hand, we know that it's often the case that current models overfit like crazy, and it works pretty well. And indeed, there was a sort of nice paper by our colleague, Vitaly Feldman, that showed that there were natural problems where memorization of training labels was really necessary. And it wasn't even specific to a particular architecture or style of learning, form of learning algorithm. It's just like fundamental to the problem. Any algorithm that's sufficiently accurate has to be. Okay. So, that work looked at this sort of interpolation where you fit the labels of your data in a supervised problem. What we're going to look at is not just memorizing labels, but memorizing the actual features, nearly entire descriptions of the training examples. Okay, and of course, to even maybe like one of the interesting questions we had to answer along the way to like writing this paper is, well, what exactly do we even mean by this question? Like, what do we mean by a statement that we memorize examples? When you're supposed to be learning something about the problem, and so somehow you want to tease those apart. All right, but I'll get there in a minute. Okay, so here's the kind of, I'll give you like a first pass version of our result, which is sort of inaccurate in a pretty fundamental way, and then I'll repair it after that. Okay, but let me just first give you the basic setup. This sort of classic supervised learning setup. We've got a data set that consists of n rows drawn IID from some distribution, little p. And each row consists of d features, so these are each of which is a bit. So I've got it like a binary vector length d for each example, and a label, which could be a bit or maybe something a little more complicated. And it's not necessary for the results, but it's like helpful to think of d as even bigger than n. So it's a very high dimension set. All right, and then we've got a learning algorithm that takes these inputs and processes them and produces a classifier. And then we're going to evaluate the class. We want to measure accuracy in the sort of standard way we would do in supervised learning, where we take a test data set, a test record from the same distribution that the data came from, and run it through the classifier and check if the label the classifier predicts is the same as the label that that came with the example. Okay, so our error is just misclassification error. Okay, and the question, as I said, is that I'm interested in is sort of what, how much information about X is sort of has to be like baked into this model. Yeah. And roughly speaking, what we show is there are natural tasks. I'll try and convince you what natural means, but roughly like of the flavor that people really, solve in machine learning, such that for every learning algorithm, whose error is like close to optimal for the sort of task at hand. Let's say within some 10% prediction misclassification error of the best learning approach. Then the mutual information between the data and the classifier has to be large. Okay, and how large? Well, the data here consists of n times d bit, well, n times d plus 1 or something bits, but let's just call it n times d. And so we're getting, at least some constant fraction of that in the model. Okay, so already this is like, I think a fairly striking statement. If you sort of think about it for a little bit, like maybe you should be a little skeptical because, you know, if for example, if you already knew what distribution the data were coming from, then if the learning algorithm knew the distribution P, then it could just ignore X. It could generate its own data. It could like sample its own fresh data on its own, right? It wouldn't even have to look at the input data. So sort of as stated, this result is false, but I'll like refine it in a little bit. But first, I want to give you a flavor of like what kinds of problems this might make sense for. For what kinds of problems this phenomenon might occur. Okay, so let me give you one example. So we've got this setting where data, they come from some kind of clusters. And what I mean by a cluster, I'll call it a hypercube cluster. So these are, within each cluster, the data are drawn uniformly from some subcube of the hypercube. So there's a certain number of, a sparse set of bits that are fixed, and the remaining bits are filled in uniformly at random. Okay. And within each cluster, there's a different set of fixed bits. And the label of an example is just the name of the cluster it came from. Okay. So this is a, obviously like a binary problem. It's not exactly the kind of thing we, normally solve, but it's sort of like you can sort of see how it contains like a lot of sort of geometric learning type, like it's sort of a stylized version of a lot of kind of nearest neighbor type clustering settings where the clusters are, the points within the cluster are closer together because they share some number of bits than random points are from different clusters. Just to be clear, the labeling task is given a fresh point from one of these clusters, you have to figure out which cluster it came from. Okay, now just to give some intuition of what's going on, if I've got a cluster from where, if I'm looking at a cluster where I got lots of examples in my training data, then very quickly I'll like be able to filter out which bits are with that cluster, which bits are fixed and which ones don't matter. And I can just remember, a subset of those fixed bits, and that'll give me like a little fingerprint that I can use to identify future points from the cluster. But if I'm only given one or maybe two examples from a cluster, then I don't really have enough information to figure out which bits are fixed and which bits are random. But if I go and throw a bunch of bits out or sort of project down to some lower dimensional representation, then it, provably, but at least intuitively for now, I throw out like the good information along with the bad. I'm throwing out the baby with the bathwater. And so what, basically in a nutshell, what we argue is in these settings where you've got these sort of sparsely represented subpopulations, then you have to remember all sorts of information about your examples, even though it's like totally irrelevant to the task at hand in the long run. Like if you had more data, you would totally just throw all this stuff out, almost everything. But you don't necessarily have more data, and so you have to keep these things around. Okay, so that's just a flavor of examples. Again, questions are welcome and interruptions are welcome. I have no idea if anybody's raising their hand. All right, so let's sort of, here's the first pass statement I gave you. Again, this one as written is false, but let me now give you a statement that's actually true. All right, so the first thing I told you is that like, in order to prove any statement like this, we somehow need the learning algorithm not to know the problem, the exact distribution for which it needs to solve this clustering problem, this labeling or supervised, prediction problem. Okay, so what we'll do is we'll assume there's some meta distribution Q on problem instances, and a problem instance is a distribution on labeled examples. And so that's the thing that it's like a population, a big population, and this Q is like a distribution over those distributions. So the algorithm is allowed to know the kind of meta distribution, but not the specific instance it has to solve, because we want to force the algorithm to actually look at its data. All right, and so now there's a natural task, and this task Q depends on the dimension and also on the sample size, such that for every algorithm that achieves error close to the optimal error for this metatask Q, then the mutual information between the model and the data, even conditioned, even to an observer that knows the task at hand, that actually understands the population from which the data were sampled, has to be very large. Okay, so again, little p is a problem instance. It's a distribution on labeled examples. Big P is a random variable, which takes values in these problem instances, and it's chosen from this meta distribution. And here, the optimal error, this is sort of the optimal error we get for the error of the optimal learning algorithm, the sort of Bayes optimal strategy if you know Q, but not the specific population you're dealing with. Okay, so this is actually a theorem you can take home. Actually, a true state. Okay, I guess the only part that's not theorem-y about this is like whether or not this constitutes a natural task. Obviously that's a subjective assessment. All right, so so the point is that by conditioning on the problem description, we're basically saying like the model has to be storing stuff that is not actually relevant to the prediction problem at hand. Like if it had more data, it could eventually not have this problem. But because it's dealing with a finite amount of data, it may have to store extra information, or for these problems, it has to store extra information if it wants to sort of do as well as it could for the amount of data it has, which is normally what we're often, what we're trying to do. All right. Okay, so this is the first, first true version of the result. We can actually refine it a little bit and say even more about like what exactly we're trying to store, what exactly is being stored. Okay. And so specifically, what we actually show is that like for these problems, for every data set, there's a subset of the rows that are kind of special examples. So these are what we call singletons. So these are examples that are somehow lone representatives of their little subpopulation. And there are two properties that this set has. So first of all, the set is typically big. So it's generally a constant fraction of the data set overall. And secondly, for every learning algorithm that is sufficiently accurate, the information about this subset is basically the number of bits in those examples up to some small correction factor that depends on how accurate you are. So what this is saying is that for these problems, the learner stores an essentially complete description of like this large subset of examples. Okay, at least in the Shannon information sense. Now, one of the things that's like, there are a number of interesting points to make about this result, I think. One of them is that we don't know how to make it necessarily algorithmic in all cases. So this is an information-theoretic statement. That doesn't mean that there's an efficient extraction algorithm. At least we don't know how to show there is one. Although, as I'll talk about in a few minutes, we have some experiments suggesting that actually, typically, at least for the learning algorithms that we use on a day-to-day basis, there really is an efficient extractor, and it's not that hard to build. Yeah, so this is the main result. Okay, questions? I'll keep going. Okay, so there's obviously other related work. The most salient is this work of Feldman that sort of shows that labels have to be memorized. There's this really nice line of work on learners that leak little information about their inputs, which is sort of related to differentially private learning. And in particular, there's this kind of work on lower bounds for pack-based learning by Livni and Moran that came out around the same time, about a year earlier. And there's a way to reinterpret what they do in the setting we consider. Or not for the problem. Well, yes, for not exactly for the problems we consider, whatever. They get a lower bound of something like n log d. It's maybe n log d, n log d. It's not entirely clear what the best thing you can get with their argument, but it's not better than n log d, versus theta n times d, which is sort of the kind of thing we're getting. There's another equally interesting line of work on representation complexity, where people look at well, how big a model do you need just to represent an accurate answer for the problem at hand? Okay, so this is actually, what these works actually do is they lower bound the mutual information between an accurate model and the problem you're trying to solve, as opposed to the mutual information between the model and the data. But also, in our settings, P is small. So it's n, it's little o of n times d. It's n square root of d or something like that. So these are, the issue is not that it does not exist. In our setting, there exists a small model to explain a small predictor that would do very well. In fact, there exists a predictor of size about n times log d for these problems. Because you just need to kind of remember a few fixed positions to nail down a cluster. So it's not that the model has to be big to solve the problem. It just has to be big to solve the problem using a limited amount of data. And this is related to some time-space trade-offs for learning. I'll get to that a little later, and maybe to some other stuff that if you're willing to cast a wider net, then there's lots of other related interesting topics like information bottlenecks, minimum description length learning and stuff. But maybe let me talk about a different sort of category of implications of the relations to this work, what this work tells us, which is I got into this thinking, a lot of my work is on private data analysis, and sort of that's what got me thinking about the potential necessity of this type of memorization. But there's this other interesting aspect to it, which is trying to understand why we train such huge models these days, right? And there are lots of explanations, but if you look at sort of the theory literature on this, there's broadly three categories of explanations that I've seen, although I'd be happy to hear about others. One, the basic simplest one is just expressivity. The bigger the model, the more functions you represent. Right? That's more or less self-explanatory. Another kind of remarkable feature of neural networks is that as you expand the number of wires and nodes in the network, it often kind of flattens out the optimization landscape in a way that allows you to use very simple optimization algorithms like SGD and its variance, momentum and stuff like that. And so often increasing the model makes optimization easier, which is kind of counterintuitive, but cool. And then another related thing is that once you're using these very simple models like SGD, very simple optimization algorithms like SGD, they give you some kind of implicit regularization that means that the model generalizes well, even though it's got this huge description. But I'd like to suggest that our results, point at a very different, an alternative, very different explanation that's complementary to the others, which is that large models store information, allow us to store information about our training examples, whose usefulness just isn't yet understood, because we don't have enough data. For example, as in our work, where there's sort of small populations, small subpopulations. But also, I think, this isn't reflected in our work, but I think it's a reasonable theory, is that a lot of the kind of reason for the hugeness of modern models comes from the fact that we want to adapt the same model to many different tasks that we haven't yet encountered. And so we sort of store all this information about our training data. The model ends up being like a relatively efficient, only slightly compressed representation of the entire data set, because that allows us to go back and change our minds later about what exactly we wanted to do. All right, I've got a few minutes left. I'm happy to take questions or not.
Are there questions? But Adam, why don't you finish and then we'll have questions.
Yeah, sure. Yeah, I just like the format doesn't allow me to see if there.
I know. Sorry.
Okay, so let's see. I'm a little short on time. We implemented this for some simple models, simple distributions to see what happens. I guess I'll just flash like this one picture here, which is like, if you look over here, we're training some, multi-layer, just two-layer neural network on the problem that's basically the one that comes up in our theorems. And what you get is this sort of really interesting thing where as you train the model, the training error gets very small, and then the attack error gets very small. So you start to be able to like recover very faithful descriptions of individual training examples. And then only after that does the actual model performance start to decrease a lot. Like you have to kind of memorize, at least in these models, they memorize kind of long before they are actually producing good predictions.
I have a question. What exactly is the attack here?
Okay, what's the attack? So yeah, I skipped over that. I was in a hurry, but basically what you're doing is you look at the model and you try to find you try to find examples that produce very confident predictions. So what you do is you sort of start with like a, roughly speaking, a random example, and then you sort of search locally to improve the model's confidence in whatever prediction it's making. And then it'll tend to drift close to one of the actual training examples. At least for certain subpopulations, for the subpopulations where there's only one training example in the data.
So you're assuming the attacker has some prior knowledge on this P or Q or?
Well, on Q, yeah. I mean, I guess this particular algorithm is somewhat tailored to the setting. So there's you don't assume the attacker knows the population, but that it knows kind of the class of problems your model is trying to solve, and like what kind of data your model was probably trained on. Okay, let's see. I'm more or less done. Yeah, maybe I guess I'll have to skip over this. We have another follow-up paper that looks at a similar family of examples, like a similar family of problems, but looks at not final model memorization, but intermediate states during training. And again, shows that these intermediate states, even though they're not predictive models, like you don't have to make predictions per se as you're training. These intermediate states have to be very big. And again, there's a sort of an information-theoretic explanation for the fact that your intermediate states for these problems need to store lots of information about, on average at least, about examples they've seen during the course of training. And so this gives us, the sort of time-space trade-offs So time-space trade-offs were previously known for other machine learning problems that are maybe somewhat less natural, like things based on parity, for example, more algebraic problems. But our techniques give trade-offs for more natural problems like regression, sparse regression type problems that are like smell a lot more like the kinds of things one does in practice. But maybe I'll skip over that since I'm out of time, and I'll just go back to this sort of last slide, this one, and I'll leave you with this thought that I think information theory has a lot to offer in terms of shining a light on what's going on inside these big models. And I think these results on memorization are kind of, I'm not, there's been lots of efforts to use information theory to shine a light on what's going on inside, big models. But this is sort of a qualitatively different take, I think, from what people elsewhere in the literature have done. And I will stop there and say thank you very much for listening.
Time for a couple of questions. Yes, Oliver.
Thanks, Adam. I hope you can hear me.
Yeah.
So you mentioned that you kind of got to this problem thinking about privacy, and it seems like your result seems to suggest that privacy is like fundamentally impossible. Is that, do you?
Yeah, I mean, it's, we have lots of lower bounds for various kinds of privacy, on like the sample complexity for solving problems under various privacy constraints, right? Privacy type constraints. In fact, Jaidev's talk just before mine gave you other such lower bounds at, at some level. I think, I was interested in sort of much more extreme examples of a privacy failure than just, an inference attack or something like that. So this is sort of the really extreme version. Now, the good news here, the positive news that's hidden in these examples is that in all the problems, at least we can think of, where these phenomena happen, if you're willing to accept that you'll get the performance you would have gotten with less data. Like if I'm willing to multiply my data set size by 10, and like I'm willing to use 10 n examples, but get the accuracy I would have gotten with n, then you can get away without all these problems, at least for the specific examples we know. So there's sort of a hidden silver lining, which is that, if you're willing to kind of accept that you can't use all your data optimally, then often these problems kind of go away. But if as is the case in a lot of the time, you really want to like extract every last bit out of the data you have, then at least there are not crazy settings where that means you're basically going to have to like memorize big chunks of your data.
Thank you. Actually, before Adam leaves, I want to say something. When the three of us were, it's a way of thanking you, but I'm going to say something. When the three of us started talking about this outreach, we considered various locations, especially ASU. But in 2019, Adam and Katrina Leggett and a bunch of people organized a semester-long workshop. I don't know, semester-long program
Yeah.
on privacy here at the Simons Institute, and I had the privilege of being invited to actually organize a mini workshop with Flavio and Peter and others, and also come back and give some talks. And Simons is such an amazing place. So I'm glad I convinced them that we should come to Simons. I don't think we could have done this as well. It's just been so smooth. So Adam, I have to thank you for creating.
Oh, well, yeah, thank you. Well, thank you for your participation in that program and for the workshop you organized at the time, and for the speakers you brought, some of whom are at this current workshop also. So thank you to all of you who spoke. But yeah, Simons is an amazing place, and I'll take the opportunity to thank both the organizers of this workshop and the Simons staff who do such a fantastic job.
I guess the only minor feedback is they have cameras in the front, and they combine 3 cameras and do some really awesome stuff.
Yeah, I mean, there's a limit, unfortunately. If it had been feasible logistically for me to get on an airplane and show up to give the talk in person, I would have preferred to do that. I would have enjoyed the workshop a lot more personally, but such is life.
Thank you for the talk. And
all right. Thank you, and I'm happy to answer questions offline or interact if people have other questions. Anyway, thanks again. Bye-bye.